Hello everyone, this is Martha with the Academic Support Center at Raritan Valley Community College. This video is going to be about Descartes' Rule of Signs, and this one can be a little tricky. The whole reason that we want to know this is it can help us narrow down our list of possible real zeros. Now, this isn't the complex or the imaginary ones. These are the real zeros where it crosses the x-axis. So there's two ways that it helps us. It helps us give a pretty good count of the positive real zeros and the positive negative zeros. So, or positive meaning like positive 3, positive 6, positive 20, any of those. For the negatives, it would be negative 1, negative 4, negative 3, negative 4. So it helps us give how many of each number, and it can help us narrow down as we go. So we're going to look at the positive first because that's a little bit easier. With the positive real zeros, we just count the sign changes in the original equation. And that's the number of positive real zeros, or that number minus 2. And why minus 2? And it's because the complex zeros come in conjugate pairs or in pairs of 2. And that's pretty much why. So let's give an example of this. We've got 3x to the 7th minus 2x to the 5th minus 4, or x to the 4th. Let's make that a little neater. X to the 4th plus 7x squared plus x minus 3. Now we look at our original one and we say, okay, how many sign changes do we have? This goes from a positive to a negative, so that's one sign change. This is negative 2, negative 1, stays the same. Negative to a positive, there's another sign change. Positive 7, positive 1, both still positive signs, so not a sign change. And then positive 1, negative 3, positive, negative, we have a sign change. So there are 3 positive real zeros or 1 if we have a conjugate pair in there. Let's look at another one just for practice. Negative 7x to the 6th minus 5x to the 4th plus x plus 9. Now let's look, we've got negative 7, negative 5. So that's negative, negative, not a sign change there. Negative 5, positive 1. Hey, there's a sign change, so there's one sign change. And then positive 1, positive 9. It's the same. So we have one possible positive real zero. And we can't really subtract 2 from that, so that's why it's just 1. So we're going to take those same equations and we're going to, for the number of negative real zeros, what we do is we subtract, wherever we have x, we put in negative x and count the sign changes. Something that's important to remember here, negative, if we have negative x and it's squared, it's going to go positive. Or any even integer up here, if we've got negative 1 times negative 1, it's going to be positive. Negative 3 times negative 3, it's going to be positive. And because we've got kind of matched negatives, our answer is going to be positive. Now, if we've got a negative, something negative to an odd power, like 3, 5, 7, it's going to be negative. So negative 1 times negative 1 times negative 1 is going to be positive 1. And knowing this can help us as we go forward. So let's look at these equations again. we've got 3x to the 7th minus 2x to the 5th minus x to the 4th plus 7x squared plus x minus 3. So we're going to, just for time's sake, talk through this a little bit, right? We've got a positive. If we put negative x in for the 7th, we're going to end up with negative. So this becomes negative. Again, if we put negative x in for this x to the 5th, it's going to be negative. So negative and a negative becomes positive. Positive 2x to the 5th. Now if we put a negative x in here, because it's to an even power, the sign's going to stay the same. So it's going to be minus x to the 4th. The same thing with this. If we put in a negative x here, because it's to an even power, the sign doesn't change. So we're left with positive 7x squared. Now this is x to the 1, or just if we put negative x in there in place, we're going to have minus x, and then minus 3. And then we take and we count our sign changes after we've substituted in this negative x. So here we've got negative 3x7, x to the 7th, and positive 2x to the 5th. So here we've got one sign change. Positive to a negative, we've got another sign change. Negative to a positive, another one. This one's going to have a lot of negative real zeros. Positive, negative, 4, negative, negative, those signs didn't change. So we have 4 possible negative real zeros, or because we subtract that 2 again, or 2. And that can help us narrow down when we're trying to use synthetic division to find all the changes. So now let's take a look at our second equation. Negative 7x to the 6th minus 5x to the 4th plus x plus 9. And we're going to put in our negative x's here. Now this is negative 7x to the 6th. Because it's x to the 6th, it's an even power, and so that's not going to change. So we're going to be left with negative x to the 6th. And then if we put negative x in for negative 5x to the 4th, because it's raised to the 4th or an even power, it's not going to have a sign change. So it's negative 5x to the 4th. Now if we put negative x in for plus x, we will get negative x. And then plus 9. So now that we've put in that negative x, let's count the sign changes. Negative 7x minus 5x, no sign change there. Negative 5x, negative 1. No sign change there, but we've got 1. So this equation has one negative real zero. Descartes' rule of sign can be a little tricky, but knowing that we take the original equation and count the sign changes, and those are the positive number of possible positive real zeros. And remember to take the number that we get, it's either that or we take and subtract that number by 2 because of conjugate pairs. Now if we're looking for negative real zeros, we substitute in negative x wherever we have x, and we work that out in the equation, and then we count the sign changes from there. I hope this is helpful. Have a great day.